it's really deep in there, so they couldn't even get it out. So I have to come back like on Tuesday or something. But yeah, it's pretty annoying.
Are you
But
gonna have to like get surgery for it, do you
um,
think, or no?
no, yeah, I don't think so. I think they gave me some like drops which will uh work against like the inflammation of the canal to make it wider because right
Mhm.
now it's inflamed because I stupidly like trying to like get it out myself. So like my canal is inflamed, so it's like narrower. And so, and the obstruction's like right on my eardrum, so it's super painful when they try
Oh,
to get it out. But yeah,
ouch.
it's pretty annoying. It's pretty annoying. Just started like Tuesday night, like after I showered.
Well, I hope it gets better the next time you go.
Seriously, yeah. So okay, yeah. What's up? What's new with you?
Okay, so I took the first Altius full length
Mhm.
and I put my scores in the spreadsheet. But like they were the same as what I told you.
Mhm.
I think I mean, I know you said that Altius is a little more difficult than AMC, but
Yeah, it's a lot more difficult. So wait, it seems like you got a 506 in like AMC full length one, and then right?
yeah, I got a 506 in AAMC, and then this one I got a 508, which I guess is good that
Oh,
it
that's
improved a bit.
yeah, it's an improvement, especially considering it's a tougher test.
Mhm.
But go on. What you're saying?
I think like I'm most not nervous, but apprehensive about chem because honestly, with bio too, because I'm still in the process of reviewing all of the questions now. I have like 10 more to review for bio. And I'm seeing like,
I may not
sorry,
have been clear in this, but when you're doing the blind review, you're only doing the ones that you got wrong the first time.
um,
Sorry, I should
because
have.
I, so, yeah, because it was taking like quite a long time to do everything.
Yeah.
But honestly, like when I was reviewing like I reviewed the entire test for just chem and bio, and like texted you earlier, like I actually went down in chem because there were some questions that I was overanalyzing,
Yeah.
um, which has been a common theme for me, like ever since I started studying. I kind of like overthink questions. Like there was one bio question where the answer was explicitly stated in the passage, but I thought it would be too easy to answer it that way. So then I like picked the wrong answer.
Got it. Got it.
Um, I
So,
all oh sorry. I just wanted to say I also like have been noticing a trend that a lot of the things I'm getting wrong is because I'm not understanding the passage concept, like the overall idea of it. Um, so I guess I need some strategies on how to better like understand it, especially under time constraint, because a lot of the stuff there is like stuff I have to review content wise, but it's mostly conceptually understanding what they're writing about.
got it. So, all right. So we're able to, I guess, finish reviewing the Jack Weston content diagnostic.
I like put a pause on that so that I could take the full length. So I'm gonna finish reviewing like everything from the full length now that it's fresh in my brain and then go back to Jack Weston's.
Got it. So yeah, so okay. So yeah, now you know that it's just the ones you got wrong. Because that way, you can't get a lower score.
Yeah.
I'm sorry, I should have made that
No, that's okay.
describe when I talked about what the blind review was. So okay, okay. Because yeah, the idea behind the blind review is just that there's going to be questions you got wrong simply because you ran out of time and so you want to try to help out. But yeah, all right. What would you like to go over today?
I think mostly chem and then chem physics, and then if we have time, I have questions in bio. Um, but I can pull up my question. What'd you say?
How was timing?
Timing, I was able to get to every question, but I wasn't able to review anything except psych.
Mhm.
So like I saw question 59 for
Yeah.
everything, but I was like rushed for time at the end.
Yeah.
Um but I think the um like the marks that you like timing marks that you said were helpful. So I'm gonna keep doing that. But I haven't had time to review anything during the test yet.
Got it. Okay. So yeah, the thing with the without the timer going, got it. Okay. And the checkpoints were useful, timing checkpoints. Uh, okay. Yep. So yeah, we can go over any of the stuff.
I'll share my screen. Um, okay, so I had another issue with electrochemistry.
Mhm.
I think this one though, I had to review like the positive and what the positive and the negative meant of a battery. But I was confused because to me it made sense that if the electrons are leaving, that end of the battery would be more positive because the electrons are leaving.
Yeah, so it depends on um where you're starting out because I think I drew like a battery for you last time, right?
Yeah.
Like this. So, you know, this what? Sorry, I don't know why I think my something, but so oh, my battery thing is still here. So this positive end, negative end. So the thing is that a battery, you know, requires there to be a charge separation in
Mhm.
order for us to convert this into an electric signal or electricity. So you will start off with a battery having its negative end have an excess of electrons
Okay.
and the positive end having, like a deficit of electrons.
Right. And you were saying like as the battery gets depleted, like they kind of switch and like the other side becomes the negative and positive.
Yeah, so this battery has this charge separation. I mean, there's like kind of this like impermeable membrane between the two. And you're going to have like so you can't have, you know, stuff moving within that battery because of this like, membrane here. So when you connect both sides to a current carrying wire, you're going to have the side that's negatively charged with that excess of electrons, you know, have the electrons drawn to the positive end, which has, too few electrons. And that'll
Mhm.
just happen spontaneously because that's just naturally what's happening. Um, and this will happen until there's an equilibrium that's established. So your equilibrium will mean that enough of the electrons have left the negative end to leave that with a charge of 0, and enough electrons have reached the positive end for that to have also a charge of 0. This is at equilibrium, and this is when you have a dead battery,
Okay.
right? So what you can do then is you can charge your dead battery by plugging it into an external source of electricity, like whether it's like an outlet, it could even be like another battery. So like let's say this is like the plug, you plug it in, and when you plug it in, you're forcing this like electrochemical cell to run in reverse by having, so when we run it backwards, right, we're gonna have it so that these electrons that come in from this electric source, like how do we, I mean, if it was just, 0, 0, like at equilibrium, like, there's no real reason for it to choose one end or the other end. So what happens is we momentarily have the bottom end positive and the top end negative, just because we're running it backwards. And when you run it backwards, you have electrons going to this bottom end here.
Okay.
Don't want it to go to the top end. So this happens until it reestablishes the chemical gradient, the separation of charge between the positive end and the negative end. So basically, this here is your electrochemical cell, which, has a bunch of other words like galvanic cell, voltaic cell, concentration cell. I think those are the ones I can think of.
Mhm.
So that's just how a battery works, which is that it takes advantage of that separation of charge, which we can call chemical energy or a chemical gradient, and it converts it into an electrical energy or electricity, which is electrons running through like this wire. So
Okay.
yeah, so that the idea is um that you start off with electrons moving from the site of a surplus of electrons to the site of like a deficit of electrons. So a negative to positive until it's at equilibrium. And then if you want, you can plug it into an external source. And then so like when you plug it into an external source here, this now is called an electrolytic cell. And
Mhm.
that's where, you know, the signs flip and the it's no longer spontaneous. So and it's conversion of electrical energy to chemical energy.
Okay. So then in this case, this was the diagram.
Mhm.
So this was the diagram they were using, and they were just asking like which is the positive terminal.
Mhm.
Um, so I guess because it said that the electrons pass from the nanowires to the FSNO2 electrode to the top,
Mhm.
then this would be negative, and then that would be positive. Like the top would be positive.
Mhm.
Okay. I think this might have been like one where I was overthinking.
Yeah, right. Because it's like, okay, um, if it's negative, then electrons are gonna leave there, but as it leaves there, it gets less negative. And if it's leaving something, so yeah, it can get a little confusing with like at what stage of the battery, are we at?
Okay.
So yeah.
Um, then the next one. Need to see what I was doing here.
I'm putting in the chat a pretty good image of the two types of, yeah, galvanic versus electrolytic. So the electrolytic one you can see involves this external source of electricity.
Yeah, okay. Um, that. Okay. The next one. Okay, this one I think is just more about like strategy. There was a question. I kind of like flipped the two questions where this one and then a different one were asking similar things, but one is asking about prior knowledge and the other one was asking about something within the passage, and I flipped them. And I think I just have trouble like I don't know, like under miss I keep missing keywords of questions or something in the passage. And I'm wondering if you had like
Yeah.
strategies for that.
Yeah, so we could actually go like over this passage and kind of talk about like I guess yeah, how to like approach it. So like um so here, so I'll like kind of read it and I'll kind of like talk to you about like what I'm thinking out loud. So like, okay, the size, weight, and charge life of the batteries used in implanted medical devices are limiting factors in device implementation. Researchers investigated the use of solar cells implanted below the skin as an alternative power source. Um, so anytime they talk about batteries, we want to be thinking electrochemical cell and all that stuff, you know, spontaneous. What would a cell potential be for, a battery? Um, like positive, negative, zero.
Is it is it positive?
Uh-huh. So are you thinking what formula are you thinking?
Like the cathode minus the anode.
Oh, I see what you're thinking. Yeah, so that's gonna give you your E cell. But how do you know like, if it's positive or negative for, electrochemicals, electrolytic?
Um,
Any other equation come to mind?
there's probably another one, but I can't think of it right now.
What about something with delta G? Something with
Mm,
delta G and maybe
Like
huh?
the ln like delta G equals.
So there's that one. Yep. That's
Mm,
gonna be with your like equilibrium equilibrium constant, but there's this one,
Oh,
right?
yeah, I need to go over that one.
Yeah. So this one is just so your Gibbs is equal to so like lowercase n is like moles of electrons, F is Faraday's constant, and then E cell is the cell potential. So for something to be, so tell me about like delta G, like what delta G has to be in order to be like spontaneous or, not spontaneous.
Well, if it's a spontaneous reaction, delta G would be negative. And if it's non-spontaneous, it would be positive. So in this case, because there's a negative in the equation, a elect like a galvanic cell is typically spontaneous, so it would need to have a positive cell potential
Yep.
versus electrolytic would have to have a negative or yeah, a negative cell potential to make Gibbs free energy positive.
Yep. Perfect. So Yep. So these are just things that you want to have like kind of like pop up in your head as you read stuff about batteries. So, okay. One experimental solar cell is a system of zinc oxide nanowires coated with dye molecules, as shown in figure one. Um, so there's some stuff about dyes that I can go into, I guess maybe some other time if it's relevant. But right now I'm just going to continue. So the nanowires are, okay, wait, as shown in figure one. Okay, and the nanowires are finger-like structures with a diameter um, of approximately 100 nanometers. Um, the dye molecules act roughly as would the leaves of a tree, absorbing light. Okay. Um, Excited electrons pass from the dye molecules into the nanowires. The electrical circuit is completed as electrons pass from the nanowires to a fluorine, I guess like silicon oxide electrode, um, bottom of figure one, through a wire to the load, and from the load to a platinum, fluorine, silicon dioxide, or whatever electrode, and through a liquid electrolyte back to the nanowires. Okay. The two electrodes are separated by 20 micrometers and have a typical area of 0.5 square centimeters. Okay, let's look at this schematic here. So we see light kind of like hitting the like this bottom part, like the fluorine silicon dioxide like thing. Uh,
Mm.
and I think I might be even wrong about that. I think that might be even selenium, not silicon.
Yeah, isn't silicon Si?
Yeah. So,
It doesn't really matter for this one, I don't think.
so okay. Um, Ew, it's tin. Okay, I was way
Oh,
so
oof.
okay. So okay, light hits this over here. Whoops. Light hits this over here, and let's go up again. On the left. So okay. You're saying that the dye molecules, zinc oxide dye, okay. Well, excited electrons pass from the dye molecules into the nanowires to a this electrode down here. Okay. Through a wire over here to this platinum thing, and through a liquid electrolyte back into the nanowires. And okay. So I guess these zinc oxide nanowires are coated with some dye, and the dye molecules absorb light and excited electrons. So like when like photons get absorbed, for like, if they have like the right energy, that would cause like an electron to be excited, right?
Mhm.
Okay. So excited electrons pass from the dye molecules into the nanowires, and from the nanowires, so I guess like it goes from like here to here and then up here, and then I guess it can then go through this. So in the background here, there's like this liquid electrolyte, which lets it kind of go back, I guess, to the, let's see, nanowires rather. So something like this. And okay, all of that stuff. And okay, so we see like essentially, I guess this pathway kind of here. Um, and it seems like, this part is losing electrons, this part is gaining electrons. All right, let's see what's below. Okay. Researchers measured the current density, which is current per electrode area, as a function of operating voltage. The results are shown in figure 2. Um, by convention, normal operating current is said to be negative. Um, okay. In order to function as a solar cell, a voltage must be chosen that results in a negative current. So we have this figure 2, current density as a function of voltage in the nanowire solar cell. So the current density is the y-axis, the voltage is the x-axis, and for this to function as a solar cell, we need to choose some voltage that will result in a current density that's negative, right?
Mhm.
So like less than zero point 0.7, right?
So when it says that
Mhm.
current is considered to be negative and you need to choose a voltage that results in a negative current,
Mhm.
is that, are they kind of saying the same thing or are they like canceling out the negative? I don't like if current is negative and you need a negative current, is that like, do you know what I'm saying? Kind of.
So so I think that what they're trying to tell us is that by so we have current density versus voltage in this figure, and by convention, current is considered to be negative. And I think that's because current by convention is actually the opposite of the flow of electrons. So like, this drawing that I made, where
Yeah.
the electrons going from the negative end to the positive end. That'll be the electron flow, but your current is in the opposite direction, right?
Yeah.
So it's like people like whatever, like Benjamin Franklin discovered like, electricity or like current way before anyone discovered like, electrons. So like current when we talk about it, right? Or like, even in a circuit like this, right? Like
Hmm.
this larger, so this is a battery in a circuit, right? And like this longer like horizontal line is your positive end and the shorter one is your negative end, right?
Yeah.
So we say current goes from this positive end to the negative end, right?
Yeah.
When we know in reality it's the electrons are going from the negative end to the positive end, but current is like when people came up with current, they treated the charges as if they're positive charges. So current and electron flow will be in opposite directions. So I think they mean like that's what they mean here by just by
Okay.
convention. That regular like normal current is considered to be negative because it's in the opposite direction of the electron flow.
Okay.
But yeah, so they're saying so like even if it wasn't like for all of that stuff, like if they're saying that this current is supposed to be negative in order for this to function as a solar cell, uh that you must choose some type of voltage that results in a negative current. And so I see that like point if we're looking at this black line that's, this much like visible light, right? It hits this zero current density line at like a voltage of like zero point 0.7, right?
Yeah.
So you would you would need to have a voltage like equal to or less than, or like less than 0.7 volts in order for you to have a negative current density, which they say, you need for in order for this to function as a solar cell.
Okay.
That makes sense?
Yeah.
Okay. All right. The efficiency of the device at various wavelengths was determined using two measures, the incident photon to electron conversion efficiency, IPCE, the like the straight line and or like filled in line, and light harvesting efficiency, LHE, dotted line. And so you see figure 3, solar cell efficiency at various wavelengths, and we can see that they both seem to be having, maximum efficiency at like maybe like 525 or something like that nanometers, right?
Mm.
So, um, and whenever you see like the wavelength, I mean, you're gonna see it constantly, but like a wavelength of light, typically in nanometers, you should know that if you're given the wavelength of light, you have everything you need to be able to solve for, if you needed to, the wavelength of that, oh, sorry, the frequency of that light as well as the energy of that light, right?
Mhm.
So, yeah, so far, that's how I guess I would look, I guess, like, or go over this passage. There weren't really any, like, kind of like proportionality stuff here, but, you know, I would just kind of take away, like, those things from the figures, like the first figure, just kind of think about the locate, like where the electrons are leaving, where they're going, and that entire thing. And then for the second figure, like being able to tell that, okay, this voltage needs to be, point less than zero point 0.7 in order for this to function as a solar cell. And then the last figure, we just saw that, at like 525 nanometers, we have like peak efficiency. So if you can come out of the passage with having like understanding like the figures that way, um, then that's good.
What I've been typically doing
Mhm.
to save time and also just because I didn't want to confuse myself is like going through the passage but like kind of skipping over the figures. Like I'll read everything but and maybe read the title, but then I kind of just skip through it. Do you think that's beneficial, or should I take the time to kind of like look at the relationships that are given in the figures?
Yeah, so I would say two things. So one, you know, this is like when it's time, time conditions and stuff, spend maybe like 15 seconds on the figure, get like a general gist of it, because a lot of times the figures are going to be more like will make something more clear than the words. Like for that first figure, like they kind of explained it, in the paragraph like above it. But it's kind of hard to like understand like exactly what they're trying to show us. So the picture kind of made that a little simpler. So I would say to spend like maybe like 15 seconds to get like a general gist of what the figures and graphs and all that stuff are kind of like trying to tell you. But if you're not getting it after like 15 seconds, then like table it, continue on with the passage, continue on with the questions. And if they ask you about the figures, then go back to the figures, of course. But, a lot of times they won't even ask you about the figures. So you don't have to spend too long trying to figure out what, like, a figure is trying to tell you. Um, so I would
Okay.
say maybe like 15 seconds, something like that. Maybe even less, maybe like 7 seconds or something like that.
Okay.
Yep.
Yeah, so then I guess like with this question, I was thinking along the lines of like which wavelength of energy has or wavelength of light has the most energy. So that's why I picked violet because I didn't even look at the figure
Hmm.
that they were given. But then a different question was asking for like which has the most energy just in general. So I guess differentiating between those two questions, like,
Yep.
is there a key word that I should have been looking for? I guess like electrical energy.
Oh yeah. Okay. So this is, common type of mistake because yes, violet. Well, I guess okay. So ultraviolet will be the highest energy, but since they said visible, you're like no, and violet.
Yeah.
So, it's very much makes sense what you chose. So I think what they're trying to say here is like if the solar cell was illuminated, right? What would produce the most, energy per photon? So we have to deal with, so it's not really just asking like what photon or what color would provide the most electrical, or I guess also the electrical, right? Because when we talk about the energy of a photon, we don't specify that it's an electrical energy, right? We just say it's the photon's energy. But since
Mhm.
they're saying electrical energy, and they're saying that this is in the solar cell, that means that they're not just asking which photon has the highest energy. They're asking in the solar cell that they are talking about in the passage, what would produce the most electrical energy per photon? And so that will then be related to the the solar cell efficiency,
Okay.
right? Because like for instance, if you had like what color was it? Like violet or something, that would be like here, right? And
Mhm.
the efficiency generally means like, so if this is 2% here, it's like whatever that energy is, like only 2% of it is actually like being made in the solar cell.
Okay.
Whereas like, in this wavelength here, it's like, 9%. So the efficiency. So yeah, them saying electrical energy as well as in the solar cell is what we want to look at here to
Okay.
different from just what has, the most energy.
Got it. Okay. Okay, this one, um, there were like a bunch of things going on. I think I originally what I was looking at was their like these molecules' ability to hydrogen bond and their mass, but they were focusing just on the retention time. And I don't know why I like didn't look. I think it was because I didn't analyze the table properly that they were giving us, and I need like a review of mass spec because like even my answer choice based off of what I was doing should technically still line up with what the correct answer was. So I think I have some issues with like analyzing mass spec data.
Okay. So let's see. So the question is okay. The question, what compound from table one has the highest boiling point? So we go to table one. Table one, they're telling us is the retention times for metabolites 3 through 9 of the in vitro experiment and the corresponding mass spec fragmentation data. Um,
So like originally I chose like the epoxide because there was like 100% abundance at like a higher mass than the other options. but I guess I'm like interpreting that wrong.
Okay, so now this is okay, so mass spec on its own won't have anything to do with boiling point, right? Like mass spec on its own is essentially you're shooting something into like something charged into like a magnetic field and it'll get deflected based on like how much it gets deflected will be based on its mass. So if it's a heavier mass, it'll deflect less um compared to like, a lighter mass. But there's nothing like related to boiling point in mass spec. So here they also talk about DC, which is gas chromatography.
But couldn't the like
Mhm.
knowing the mass spec data give you insight into the mass of the actual molecule, which can tell you whether or not it has a higher or lower boiling point?
So if boiling point was only dependent on mass, right? But we know it's dependent on intermolecular forces, right? Like, you know,
Yeah, that's like that's why I started going up here and like comparing all of the different structures to see like which would have the best ability to hydrogen bond. And I was like going back and forth. I think I was like way over analyzing everything. And I don't really know why I didn't look at the like retention time first. So yeah.
yeah. So this table one is like so talk about retention times for this in vitro experiment, which is them doing the gas chromatography, right? As well as mass spec like information, right? So we have
Mhm.
both here. So we have like, like this stuff from the mass spec and this from the gas chromatography, right?
Yeah.
So now, um, but yeah, so when it comes to trying to figure out boiling point, we must first understand that boiling point is, it's not solely determined by mass. Um, there's like intermolecular forces involved. And sure, you can look at the molecules in your figure one to kind of maybe get some type of idea. Like I can see like, you know, so yeah, like, these can form like hydrogen bonds and stuff, but that's still like something that like we can maybe make a estimate on like based on theory. Um, but since they're telling us to like look at table one, there must be some other piece of information that can more directly tell us what would have a higher boiling point. And yeah, that'll be the retention time, because that retention time involves, well, the first it involves boiling it to turn it into the gas, and then you put the gas through like the horizontal kind of like phase, stationary phase. So
Mhm.
yeah, so we're essentially, since they're telling us to look at table one, and since they're asking us about boiling point, we want to see like, okay, table one is talking about mass spec, it's talking about gas chromatography, and so what from table one um will give us insight into boiling point. So
Okay. I guess like so if it has a higher retention time, that means it stayed in the liquid phase longer, and that would mean that it has higher boiling points.
mhm.
Okay.
So yeah, see these choices here. So okay, cis cis, trans trans, benzoquinone epoxide, benzene, benzo.
So
Oh,
like these three.
okay, that, and there's nothing for benzene here, right?
Yeah, I think they just put benzene to try and like
Mhm.
mess you up.
Got it. So yeah, so we know what, benzene looks like, right? So it's, this is nitrobenzene. These are things with like benzene with things on it. So benzene by itself, likely, I mean, it'll certainly have less of a mass compared to
Yeah.
benzene with stuff on it. And it'll certainly have, no real like hydrophobic interactions. Like that's it. Not really any powerful like intermolecular bonds. So okay, so we don't have to worry about that. And if we simply look at the retention time, then I guess the trans has that highest one, right?
Yeah.
So um
Okay. Well, that makes it easier.
Mhm. So yeah, so I think the thing here is like, okay, they're telling me to look at table one. Table one has, they're saying retention time and mass spec information. And while it's true that something with a higher mass could have a higher boiling point, there's also the intermolecular forces involved, but that doesn't mean that we can look at the molecules themselves and like try to ascertain like, which thing, because we saw a couple of the molecules and some of them could make hydrogen bonds and stuff, but like how can we tell like how much better one of the things are compared to the other things? It's kind of hard to do that. So, but they're telling us, since they're telling us table one, it must be something in table one. So like, so
Okay.
you're going to like, figure one with the pictures of the different molecules, like that could be a sign of like, okay, that's not the right direction to go in because they're telling me that the answer will be in table one.
Okay.
Yeah.
And then can you just clarify, like, for the mass spec data, like like how you would interpret the numbers? Like they're saying that like 124 is the mass to charge ratio and it's 100% abundance. But how could that, like, how is that possible if there's also like the other numbers?
Uh, let's see. So I think that the relative abundance is in comparison to whichever type of ion that is produced, that's the most abundant. I think it's relative to that. So I think that the 124 M over Z thing is the most abundant. So that's going to be for the 124, 100% of that. And relative to that, it's going to be like the other ones will be like, I guess, like, yeah, 17 and all these other stuff. Like they don't have to, they don't have to add up to 100. It's just that the one that is 100 is is established as like your max, I guess. And everything.
So is that the one that's 100 is like your original molecule, like before things get broken up, kind of?
Oh, it'll be your base peak, like your tallest peak. So if it's like something like, abundance on the y-axis and your like MZ on the x-axis, and let's say we had I'm gonna do this one, so like let's see, like 53, 81, 94, 110. So the 81, so like this is going to be like 100. The 81 is going to be like at 100. And yeah, the 53 would be like whatever, like 77 here. The 94 would be like 2, like super tiny, and then like the 110 would be like 47, something like that. So so basically the one whose relative abundance is 100 is your base peak, which is the highest peak at 100%, and everything else is relative to that.
And when it's at 100%, what does that mean exactly?
So so whatever amount you have of that most abundant thing, like honestly, like let's say we had like out of like the total, like I don't know, like 85% at the mass per charge or mass M over Z thing, um 81. Like this, like let's say this is like what we actually have, like 85% is 81, and that's the highest. We would establish this 81 as 100%, and everything else will be relative to that. It's like kind of like when you normalize something, you
Okay.
establish like, you know, like let's say that they're something that talked about like um I remember there's like a passage that was like talking about like I think like G actin can turn into F actin, and some table that measure like you can either be one or the other. So and some table measured like the amount of G actin as like let's say like zero point 0.7, and they normalized it so that highest amount of G actin, whatever that amount is considered to be one, and so this is just relative to that.
Okay. And like that number, like the 81 would just be like the mass of the molecule that's most like prominent or the one that got deflected the most?
Oh, so the uh so whichever one has the highest mass or M over Z will be deflected the least, right? Because um did we do something where we had like, the magnetic force and
Yeah.
or like a charged particle that's in a external magnetic field, it produces a centripetal force, right?
Mhm.
So something like this. And we essentially got like um something like this. Like the radius is proportional to mv over qb. So what that means is like okay, let's say that this is our magnetic field going into the page, and this is our molecule. It's gonna deflect and hit this, like, let's say this like kind of wall here. And the heavier it is, the wider this deflection, because this R is like this, the radius of this, circular motion. Like if the wall wasn't there, it would be like, the circle, right?
So then in that case, why wouldn't the heaviest mo like the in this example the 110, like why wouldn't that one always be the 100%?
Oh, so okay, so this shows you that the heavier the molecule, the more it will be deflected by the mass spectrometer. Um,
Mhm.
but what they're giving us here are like the relative abundances of each. So this MZ stuff here, it's not really telling us like anything about the radius or anything like that. It's just telling us how much of each we have. So like for the cis here, yes, this 110 like mass over Z, like that's going to deflect the least and give you the largest R radius of, deflection, right? Um, but the abundance of it, how much we actually have, is 47% of how much we have the most of, which is the 81 mass.
Okay. And so depending on like whichever one we have the most of,
Mhm.
that's like that represents like an ion, or like if the molecule broke up and it's like a smaller portion of the molecule.
Uh-huh. Yeah, so there could be like, in mass spec, since we can like break things up into these smaller fragments. But yeah, ultimately, like the mass spec works like this. Like that's how it works. But the values that you get will range in mass, and the relative abundances will just be relative to whichever one has the highest abundance. Like we establish that as just being 100%. So everything is relative to whatever you have the most of.
Okay.
And there's like no real relationship between mass, like of the fragment, and abundance of it.
Okay. All right. So then I think next question. Oh, this one, same passage. Um, I'm trying to see. Oh, I think it was just like overall still like the mass spec confusion and like what each answer choice means, or like why you can rule something out. Because I wasn't sure how you could rule out C and D from this.
Okay. Let's see. What do the mass spectral fragmentation data for the buconaldehyde isomers reveal about the relative stability of geometric isomers under electron impact ionization? Okay. So yeah, so in your mass spec, you're going to ionize the thing, because if you didn't, it wouldn't be able to move in an electric field or magnetic field or anything like that. So we definitely ionize it. And and if we have something that's more stable, um, it should be more abundant, right? Because
Mhm.
if it wasn't that stable, then it's not going to exist the way it is, and you'll have less of it. So we're gonna see that, yeah, that the more abundant stuff will be more stable.
So then when it's saying that the trans is more stable than the cis geometry, um,
Mhm.
is that just because the mass was like the larger mass um was 100 for trans versus like the cis, the 81 was the most abundant?
Yep.
Okay. And then I guess continuing down, um the trans geometry would have a higher boiling point. Um, but it had a bigger retention time. So it wouldn't it have a higher boiling point?
Yeah, so you're asking about boiling point comparing trans to the cis system.
Yeah, like to rule out B, it's saying that the trans geometry has a higher boiling point than the cis geometry,
Mm,
which would be true,
yep.
right?
Yeah. So this is, so you're gonna see a lot of things that are true, but don't answer the question. That can be tricky. So it
Mhm.
is true that the trans-trans geometry results in a higher boiling point than the cis-cis geometry simply based on retention factor or retention values. Uh, but that doesn't
Oh,
much about like the stability of something.
okay.
Mhm.
And I guess because it's asking about the mass spec data specifically.
Yeah, they're asking about the relative stability, right?
Okay.
So, you know, this is more stable. This is just saying a higher boiling point. This is saying one type of bond breaking is favored in cis-cis or something, and then the next one's talking about another thing is type of double bond cleavage is more favored. But yeah, we're being asked about relative stability of the isomers.
Why would you be able to get rid of C and D? Like, if we're talking about stability, couldn't it, like, if you're talking about cleavage of a bond, couldn't that also indicate stability, like whether the bond gets cleaved or not?
Uh, I mean, if a bond gets cleaved, right, we don't know like yeah, we can't really figure out too much about stability. I mean, if they're saying that the cleavage of a C1 C2 bond is more favored by a cis-cis geometry than a trans-trans geometry, um like that just tells you that this bond is more likely to break for that type of molecule. Um, but I don't know how that would help us in terms of figuring out how stable something is,
Okay.
right? I think what if we see that I think the molecule is it here, the like this.
Yeah, these two.
So like C1, C2, C1, C2. So if the this is cis I think, and then this is cis trans or is it trans? I think it's trans. Um yeah. Like yeah, whether something is more likely to undergo cleavage or not doesn't tell us much about the stability of that molecule. Especially because it's like, all right, are we talking about stability after the cleavage or less, or before the cleavage? Like, so yeah, I think that the cleavage doesn't really tell us much about stability of something.
Okay, so I guess I should just automatically associate mass spec with stability, like being
Mass
able to,
mass spec abundance with stability. Yep.
okay.
If something is more abundant, it means that, well, it's there, like it exists the way it is. And if it exists the way it is, then compared to things that, you know, like if you have something, you don't even know what it is, and you have 100% of it, and then you have another thing, don't know what it is, but you have like 50% of it. We can safely say that the thing that you have 100% of is more stable because it exists the way it is, like
Mhm.
right now, compared to the other one, which is just if you have 50% of it, which means 50% is gone.
Okay.
So I would relate that. So what we can do is like retention factor for gas chromatography is proportional to boiling point, and mass spec abundance, like whichever molecule it is proportional to stability.
Okay.
Yeah.
That makes sense.
Hmm.
Okay. Next question. Oh, this one, I think I was having trouble with conceptualizing the passage again.
Yeah.
Um,
Be right back. One second.
Okay.
All right.
Um, this one had a lot to do with disordered versus ordered enzymes and whether one or the other is more active. And I wasn't sure if like that's a concept that we have to know, like disorder means that it's more active or inactive versus the other, or if that's just like something from the passage that we needed to know.
Okay, let's see. I'll read the passage. If you can like, let's say maximize it, yeah. Maybe like zoom out like a little bit, like
Oh, how do you?
or yeah. You it's like it's like I don't know what it is for Mac. It's like either option or something. Like, whatever the alt equivalent is, or sorry, the control equivalent, command maybe. Yeah.
Oh,
Mhm.
okay.
Okay, let's see. So the primary glucose sensor is pancreatic glucokinase. Kinase is buzzword, super high yield stuff. It's like transferase uses STY uh, to transfer like the gamma phosphate. Okay, an isozyme of hexokinase. Okay, that's like the first one in glycolysis. Um, Glucokinase activity stimulates insulin secretion from the pancreatic beta cells in order to maintain blood glucose homeostasis. GCK is allosterically regulated and exhibits moderate cooperativity with glucose, but GCK is not inhibited by glucose 6 phosphate. What do they mean when they say like, it's allosterically regulated? Yeah.
It means that the inhibitor regulates the enzyme, like not on the active site, like on a site um, on the enzyme, but not the main active site for the substrate.
Yep. So to like attach, it'll do something to some region that's not the active site and it'll kind of change its shape, right?
Yeah.
So, and what about cooperativity?
Cooperativity is when one ligand attaches and that like increases the affinity for more ligands to attach after.
Would you notice any type of graph like curve? Yep.
Sigmoidal curve,
What's that?
like looks like an S
Yep.
kind of versus like your normal Michaelis-Menten graph, which would just be more of a hill
Uh-huh.
shape.
Yep, yep, yep. Good. Okay. Uh, okay, so yeah, this one is not inhibited by glucose 6 phosphate, which I believe hexokinase is. So okay, unlike other hexokinases, GCK is not oligomeric. Oh, okay. What does that mean?
It's a monomer. It doesn't have multiple um like
Hmm.
multiple monomers together.
Yep. So it has no quaternary structure,
Quaternary structure.
no subunits. Okay. Um, which is usually yes, okay. The glucose cooperativity observed in GCK is unusual for a monomer with a single ligand binding site, and that's true. Like, usually a good example would be like hemoglobin compared to myoglobin. Like hemoglobin has multiple subunits and the sigmoidal um oxygen kind of affinity curve, whereas myoglobin is that
Hmm.
like logarithmic kind of thing. So, okay, monomer with a single ligand binding site. Okay, two theories have been proposed to explain GCK cooperativity. Theory one proposes two separate catalytic cycles arising from two different conformational states. Theory two proposes one active state with retention of the active state for a short period of time after catalytic turnover. Okay. What's that? Catalytic turnover?
Um, like when the enzyme releases the substrate, like how quickly it's able to do that.
Is it like any like particular like value that we like look out for? Well, I shouldn't say like value, but like
Yes.
is there yeah,
Um, it's I forget what the variable is, but it's not KCAT. That's catalytic efficiency, right? Or or is it catalytic turnover? I get them mixed up.
yeah. So a lot of people do. So your K-cat divided by Km would be your efficiency,
Okay.
and your K-cat on its own is turnover rate.
Okay.
So, um, yeah. So K-cat, it's kind of like your name. So maybe that can help you remember. So, but yeah. So it's the turnover rate, and usually like efficiency is some ratio of something like uh maybe that can also help, but yeah, catalytic turnover rate is the K-cat value.
Okay.
K-cat over Km is your catalytic efficiency.
Got it.
So, okay. Um, to examine these two theories, human GCK was selectively labeled at the like isoleucine 17 position and I guess tryptophan 3 position side chains and examined using NMR, two-dimensional NMR spectra, simultaneous hydrogen and carbon. Um, Usually we see like HNMR, but there's also CNMR. We don't see that as much, but it's mentioned here. Okay, we're collected in three states: unliganded, glucose bound, and glucose and AMP PMP bound. Um, okay, those are the three states. Um, and researchers concluded that the GCK small domain is intrinsically disordered. Okay. Um, what do you think of when you think of disorder?
Um, well, in this case, I was thinking of like a T state and an R state, I think it is, where like one is ordered and one is not ordered. But I don't know if I was thinking incorrectly.
Yeah, that's
Uh,
really specific. I think like the relaxed and tense and stuff states. Um, so but like disorder is entropy, right?
Yeah.
And the universe goes towards more disorder or less disorder or what?
More,
More dis
more disorder.
good. Um, and also that's what determines like your protein folding, like your tertiary structure. Um, Meaning like the if the hydrophobic residues are on exposed to the outside, and like this is like in a hydrophilic environment, um, there's an entropic penalty, it's called, for the hydrophobic like residues to be, you know, in like the water hydrophilic solvent. So to reduce that penalty, like it will fold to like sequester the hydrophobic parts on the inside to cause that folding. So, okay, so this small domain is intrinsically disordered. Binding of glucose results in the GCK small domain becoming ordered, okay? Um, so the entropy is going down here when glucose binds to it. Okay, once the enzyme product is formed, the ordered state of GCK is retained for a short period before it returns to the intrinsically disordered state. So it seems like so it seems like this GCK enzyme, there's three states for it, and this small domain is intrinsically disordered, but when it binds to glucose, it makes that small domain ordered, and then it does its job of turning the substrate into the product. And once it's done that, that small domain goes back to being disordered, right?
Okay.
Okay. Hypoglycemic hyperinsulinemia, HH, is a condition characterized by by severely low blood glucose levels due to excess insulin. What does insulin do?
It breaks down glucose.
What do you mean when you say that?
Um, like it helps glucose get reabsorbed.
What and tell me what you mean about
Like reabsorbed into the body when like it's in the bloodstream after you eat something and then the insulin breaks it down so it can be absorbed into the body and then the glucose levels decrease in your blood.
Okay, okay. So, because you know, like I know what you're saying, but like because when you say breakdown, that would be like glycolysis, right?
Yeah.
And like reabsorption, a lot of times, like in the context of like the kidney, that's going back to the blood. But I know what you're trying to say, which is from the blood to the cells, right? Because the cells are where things, cellular respiration and stuff happens, right? So insulin can take it from the blood and put it into the cells, right?
Mhm.
So, um, so yeah, if you have too much insulin, you're having really low blood glucose because insulin's job is to take that blood glucose and cause that reuptake in the cells, right?
Yeah.
That's the hypoglycemic part, low blood sugar, hypoglycemic, and then insulinemia, too much insulin. Okay. One cause of HH is a quadruple mutant GCK variant. This mutation stabilizes the alpha 13 helix in an ordered state, okay, resulting in reduced GCK cooperativity and increased affinity for glucose. Okay. If it has an increased affinity to glucose, it's probably going to be less likely to give it away, right?
Yes, but didn't it? But it's saying that it stabilizes the helix in an ordered state.
Mm-hmm.
And um hmm, I don't know. That part was just kind of confusing to me
Mm-hmm.
with that compared to what it was saying in the previous paragraph,
Mm-hmm.
where the binding of glucose makes it become ordered and then disordered again. I don't know. It was just confusing.
Yeah, yeah. So yeah, it seems like um for the regular GCK, it's intrinsically, or the small domain of it is intrinsically disordered. Binding to glucose makes it ordered. It does its thing, turning it into a product, and it goes back to disorder. So if you have this disease with this mutation, it's stabilizing the, I think, the intrinsic state from what it was, which was disordered, to what it now is, which is ordered. And that causes less of the, oh, sorry, one sec. I'll be right back. Like my dad just is dropping
Oh,
off
that's fine.
medication for me. I'll be back.
Okay.
Okay.
Um, I forget what exactly we were talking about.
Um, let's see. Um,
Oh, the two paragraphs talking about like the ordered state versus the disordered.
okay. Yeah, okay. So I guess like regular one, intrinsically disordered, binding can cause its binding of glucose ordered, and
I
then
guess the issue I was having is determining which one was the active confirmation. Like in this question, because I was associating the active confirmation with um like the order, or I don't even know what I was thinking, but like I just kept getting mixed up with like the disorder is good, but in this case it's bad when you're like trying to have a molecule attached. So I was getting them mixed up.
okay, let me look at the figure though. So let's see. So glucose x-axis, glucose concentration x-axis, y-axis is your kinetic response of the alpha 1,3 GCK variant, white box, wild type GCK, gray box, wild type GCK in the presence of a saturating activator, black box. Y axis is the, it says micromolar G6P, but the parentheses is like per second. So I think that that's your KCAT, right?
Okay.
Like that's how many molar, because you're doing glucose to glucose 6 phosphate, right? So
Hmm.
that is measuring the amount of like the product that's forming, right? And we see the wild type, it's pretty sigmoidal, and the alpha one, which we know they said has reduced cooperativity, so that should be a no, like less. It's not going to be sigmoidal anymore. Um, but now comparing that to the wild type, it's like a shift towards the right. Um, so they said an increased affinity for the glucose. Okay,
Well,
yep.
the black one was with the activator, so
Mhm.
I wasn't sure why the activator would make it less cooperative
Mhm.
versus more.
Got it. Active state. Okay, so the activator, I'm trying to think like what that could mean, but I'm gonna kind of just go into this question here. So okay, let's see. Which conclusion about normal GCK allosteric is most consistent with the data in the passage? Um, alpha 1,3 helix undergoes an order, a disorder transition, increasing GCK activity. Okay. Now, how can we determine the activity of it?
Um, like the Km or hmm, how often it's like attaching to the substrate and then letting it go again.
Okay. Um, so you said letting it go again, kind of. So it can attach to the substrate, turn it into the product, and then let it go, right?
So I guess you could measure the activity by how much product is formed.
Uh-huh. So, okay. So, and would that be like, what type of like, I guess, shift would we see in something like this, in a graph like this, I guess?
Um, if there's increased activity, more product would be formed. So would it shift to the left?
Mhm. So, so A is saying that this alpha helix undergoes an order to disorder transition. So these things, so there's a couple of things here. So since they're asking about normal GCK, this alpha 13 thing, the mutation would cause the alpha 13 to be in this ordered state, right?
So it's the alpha helix is normally in a disordered state.
Yeah, I think so. Um, so yeah. So there's that, and then also the increasing GCK activity. Let's see. Wild type this. Yeah, so I don't know about this alpha 1,3 helix undergoing a order to disorder transition leading to increased GCK activity because we know that if you have the mutation, then you can have, the stabilized ordered state. And in that stabilized ordered state, you lose the cooperativity and you increase that affinity for glucose. And if we think of the activity as, the enzyme taking the substrate and turning it into the product, like the substrate of glucose, the product of glucose 6 phosphate, I think that the affinity part should probably would should decrease, right? Because we want it to let go of the, I mean, it'll be letting go of like the glucose 6 phosphate, but I think that might be related to the glucose affinity part.
Well, in the passage, like how could reduced cooperativity increase the affinity? Because wouldn't a lower, like, wouldn't reduced cooperativity mean that it's less likely that one ligand would attract like another ligand attaching?
Um, let's see. So affinity could be like, the inverse of, let's say, like Km. So like if Km is the substrate concentration needed for, 50% of Vmax, if you have that rightward shift, you would need a larger concentration of substrate to achieve that same 50% Vmax. So a rightward shift in this that would cause would be an increase in Km, which means a decrease in your affinity, right? So I
Yeah.
think that they're telling us that this mutation for HH, which causes the alpha 13 helix to be in an ordered state that causes less of the cooperativity and increased affinity for the glucose, would cause your Km to drop, which would be like a kind of like a leftward shift. And I think that this is talking about the mutant version of the alpha 13, which is when you have that increased affinity. So now, so what I think is that if you have an increased affinity for glucose, um, that you would have a lower activity. But let me try to look at it in a different way. So if we think about or link together the alpha 13 helix um, being stabilized in that ordered state, that you have a higher glucose affinity, then we could say that if it was in a disordered state, it would have a lower affinity for the glucose, right?
Mhm.
And if this, so maybe I could do like, okay, ordered alpha 13 could be um, proportional to glucose affinity and inversely proportional to cooperativity. So, okay, so we should see that um, the GCK active site retains the active conformation after catalytic turnover. The ordered state of GCK is the predominant state under low glucose conditions. The A13 mutation increases cooperative binding of glucose to G6K. So this one, so D must be wrong, right? Because this is talking about the mutation
Yeah.
increasing cooperativity, and we know that it decreases it, so we can get rid of that. Now, A, I think, is like wrong because it's not talking about the mutation, right? Like the mutation is what stabilizes the alpha 13 helix in an ordered state, right?
But it's saying that the alpha helix is transitioning from order to disorder.
Mm-hmm. Yeah. So if they're saying in the passage that the this mutation is what causes the alpha 13 to be in an ordered state, right? Like, and it undergoes this order to disorder transition. Well, actually, I guess because I'm viewing it as like so if it's in this ordered state, I'm viewing it as like it starts off as ordered, but maybe you're seeing it in a the opposite way, where it starts disordered, but if it stabilizes the ordered state, is that kind of like you're looking at it, or?
I'm I guess I'm kind of seeing it as like the end, like in answer A, the end state is disordered. So that would be the normal, like that would be what it is normally.
Mm-hmm. What it is, no, the disorder is what it is normally, you're saying?
Yeah. Like without the mutation.
Got it. So let me see if elsewhere they talk about things that can be helpful. Two theories. Theory one, two separate catalytic cycles from different conformational states. Theory two, one active state with retention of the active state for a short period of time. Um, then the three states thing for
Like
NMC. Yep.
I think I think the difference between A and B is like theory one versus theory two.
Okay.
So I wasn't sure like how the data would like line up with being able to determine which theory was correct.
Ah, okay, okay. Theory one, two separate from different conformational states could be A, and theory two, one active state, one re with retention of the active state after the catalytic turnover is okay, okay. All right, all right. So okay, so that's what A and B are talking about. And let's see, they wrote following product release, the unliganded glucokinase persists in an ordered state until the small domain undergoes an order to disorder transition. So here, glucose, okay, once the enzyme product is formed, the ordered state is retained. Oh, okay, I think that makes sense then. So I was looking at this paragraph, which talked about the mutation, right? But this paragraph is talking about the normal GCK, right?
Okay. I guess like I was confused about that too. I just like
Mm-hmm.
I don't know. Like this passage I really like
Mm-hmm.
did not understand well.
These Altius passages are going to be really, really crazy. So it's good because it'll also like psychologically prepare you for like what would you do if you just had these really crazy passages with lots of stuff happening, lots of really ridiculous looking graphs and stuff. But I think that yes, yeah, you got it with we're looking at the two theories here and that they talk about in paragraph two. In paragraph three, they talk about regular GCK. In paragraph four, they talk about the mutated GCK. And I was like kind of spending too much time looking at the mutated one. But if we look at the regular one in paragraph three, we can see that, hey, the regular one has its, initial state disordered. And when it binds to the substrate of glucose, right, it causes it to become ordered. And then once that product is formed, the ordered state of GCK is retained for a short period before it returns to its intrinsically disordered state. So the alpha 13 helix is the reason why I was looking at that last paragraph. Um, and I was trying to see like, okay, if this last paragraph says the mutation stabilizes the alpha 13 helix in an ordered state, I was thinking, would that mean that the wild type would be the opposite. Like it would start off at a disordered state. So I was looking at it that way, but I think that you're right in that we should be looking at it in terms of the two theories, and that's pretty much exactly what we see for A is like theory one, um, or rather, yeah, theory one, and B is theory two, and we're looking for normal GCK, and the alpha 13 stuff is only relevant to the mutated variant of GCK. So that's not going to be what we really look at to answer this question. And what we really want to look at is regular GCK. And we see that in this paragraph is something that starts off disordered. And when it binds to glucose, it becomes ordered, turns glucose into glucose 6 phosphate, maintains that ordered state for a little bit before it turns back to its intrinsically disordered state. And that can repeat. So the GCK active site retains the active conformation after catalytic turnover, making the glucose into glucose.
Okay, because when I was reading the passage too, like I didn't really get that one of them was theory one and one of them was theory two. Like I just kind of understood that afterwards, like when I was reviewing and the solution explanation was talking about that. So I don't really know like when I am in the test, like I don't think I would have been able to differentiate or like kind of see that. Um, so I'm not really sure how to like fix that issue.
Oh, tell me that initial thing. You said something about like three things or something. Say that again.
Um, well, I was just like wasn't sure because when I was reading the passage, I didn't understand that A and B were talking about the different theories.
Hmm.
So like I don't know how I would have been able to differentiate those
Hmm.
when I was being timed. Like I don't know.
Got it. Got it. Yeah. So what we could do is like this. Okay, so this first paragraph is talking about how about GCK, and it's special because it can have, you know, allosteric stuff and cooperativity, um and is monomeric. Um, so that's that. Paragraph two, we introduce these two theories, and whenever you see like a passage that talks about like theories or hypotheses and stuff, which you'll see it'll be like, okay, like one group thinks that this is the way something happens, one group thinks this other way is the way that things happen. Usually that's going to be important because they're going to do experiments that can help you figure out if it's going to be theory one or theory two. So I kind of like brushed over that a bit too like quickly when I was doing my first read through. We start in paragraph three talking about, I mean, like things that can kind of get in the way of like what we are actually trying to look at. Like we're talking about, we're doing these two amino acid side chains. We're using NMR, HNMR, CNMR, like AMP, PNP bound. Like, what's that? There's so many different things happening, right? But ultimately, we're talking about, at least from here to here, we're talking about regular GCK, and that's what happens. It's intrinsically disordered. When it binds to its substrate glucose, it becomes ordered. Glucose product is formed, which is G6K, and that ordered state is retained for a short period before it goes back to intrinsically disordered state. That's for regular GCK. Last paragraph, we're talking about a mutant GCK in which this alpha 1,3 helix uh, is stabilized in an ordered state, causing this reduced cooperativity and increased affinity for glucose. Now, when I read the question here, they said, what's true about normal GCK? And when I looked at the alpha 1,3 here, I went to this last paragraph because that's the only place where they mentioned alpha 1,3, but they mention it in the mutant, and I was trying to think, okay, if this is in the mutant, does that mean that in the normal GCK that the opposite will happen? And I think I spent too much time trying to like figure it out on that lap, like figuring it out based
Yeah.
on
And I think that's like kind of what I did too. Like I went right to the answer choices and was trying to eliminate each answer choice.
Mhm.
And that made me spend a lot of time here and not really understand the question.
Yeah, yeah. So so yeah, now that I kind of like see it, I can kind of see that if we are talking about normal GCK, why don't we start by going to the paragraph that talked about normal GCK? And that means nothing about, alpha 1,3. So, and again, there's also that issue with alpha 1,3, like here in the normal GCK, but this is the mutation, so we want to make that distinction as well.
But
Um,
then I guess like for strategy, would you suggest not like if you have to refer back to the passage, like refer back to the question stem rather than the answer choices first?
I'm saying if you have to go back to the passage to refer to the question stem before the
Like refer to information in the question stem and look for that in the passage rather than like picking an answer choice and checking for it.
uh yeah. I guess spending so like what I was trying to do here was I was spending more time trying to see why like A wouldn't be an answer rather than spending my time trying to find out like B or C as possible answers. So since the question stem is talking about normal GCK, and the only mention of alpha 1,3 was in the context of the mutant GCK, I would be able to see like, okay, we're talking about A alpha 13 in A and D. We're talking about just GCK and B and C. And the passage gives us no real information about alpha 1,3 for the regular GCK. And
Mhm.
they give us a lot of information for the regular GCK that is not about alpha 1,3. So, yes, I would look at this kind of connection, normal, normal, and not even really worry about that alpha uh part. Um, because yeah, we're talking about regular. And then I guess between B and C, um, one thing is talking about retaining the active conformation. The other one is saying something that doesn't seem to be, because also when we look at this, we see, okay, retains the active. And we also want to remember, hey, we're talked about different theories here, which are always going to be important. With, and I kind of glossed over that when I first read it. So, but yeah, one of the theories here talks about retention of the active state, and another one talks about like two separate types of things, um, which is, closer to this type of transition here.
Okay.
So yeah, so you want to come out, so you want to be like, okay, we're talking about normal GCK, so we're likely going to be talking or choosing an answer choice that is not mentioning alpha 1,3. And then for the ones that we have on GCK, which one is going to be relevant to one of the theories that they proposed?
Okay.
Yeah.
All right.
Mhm.
Um, Yeah, I have to get going now.
Yeah,
So,
yeah, totally.
I guess like for a quick plan for next week, like should I be taking another full length at some point or should I push that off?
Let's see.
Because I think at this point, originally on the calendar, like we're aiming for one full length a week,
Mhm.
which I think is fine. I just have like I'm working this weekend and then I have to finish um like going through this and the Jack Weston stuff. So I want to make sure that like I finish all of the Jack Weston before I do another full length.
Got it. So the one that you did, you have, I mean, you were kind of referring to like some tab that had like your like answers and stuff. Is that in the same spreadsheet that we have?
No, that's a separate one. I think I shared it with you like at the very beginning,
Okay.
but I could reshare it with you again.
I think I found it, practice questions. Because I was gonna say, yeah, so I was gonna so okay. Like if we let's see within that I see like different AMC stuff and then
Yeah, that I did a separate tab for AAMC just because like that stuff is more reflective of what the actual test would be. So I wanted to like dive into those answers more. But
where's the stuff for like the this Altius test you took?
that's under the CP Orgo section, like all the way at the bottom.
Got it. Yeah, because I was gonna say that if you look at that and you see how many like if you made mistakes from content, right? Then you will know like, okay, this is something that, I'm gonna go over in the Jack Weston content diagnostic. And then for the questions that you got wrong because of something else, then yeah, that would be due to the other thing. So I guess that's the CIO part. Like,
Yeah.
but the C is that for content?
Oh, no, no, no. That's just
Oh,
like if
complete.
it's correct or
Oh,
incorrect.
okay. So, but anything,
But yeah, I wrote like the type of content that I have to fix, or if it's strategy, and then
hmm,
I was highlighting the stuff I got wrong on the blind review versus the not blind, like the timed one, and yeah,
got
stuff.
it. Got it. Yep. So I would say as you continue to review this, or you've already reviewed this Altius CP and BB. Um, so yeah, I guess based on that, see how many questions you got wrong because of content stuff, how much you got wrong because of other stuff. And, if you find out that there's a lot of, well, of course, for the content stuff, you're gonna like read about it and learn it before you take. So, okay, if your next test is you're probably going to take it, what, this weekend maybe or something?
Probably not until like Thursday-ish. Because tomorrow, Saturday and Sunday, I have like
Yeah.
full day shifts. Um, so I guess Monday through Wednesday, I would finish up reviewing Altius, and maybe I could do it on Thursday, the full length,
So for the reviewing of Altius, all that you have left is Psych Soc.
and cars.
Okay. Um, got it. So and for the CP and BB, for the questions that you got wrong, like you've already finished reviewing that, so like that
I
means
mean, when I like my typical review is like I go back through the questions, I determine like what kind of thing I got wrong, like if it was content or timing, pressure, stuff like that. And then after I go through that, I do another review of like actually learning the content. So I still have to do that portion
got it.
for chem and bio, like actually like reviewing the content that I missed.
Got it. Got it. Okay. Yeah. So that's okay. So that's good. So yeah, you can continue what you're doing and learn the content from the content in the questions you got wrong because of content issues. And um yeah, okay. And then you can take your next test like a week from like Thursday or something, right?
Yeah,
So
like
yeah,
that.
let's see. When are we meeting next week? Or make
I don't
oh,
actually I
if
don't
we do
know
something
when.
for Friday.
Oh, let me double check. Yeah. So I could maybe I could take the test Thursday, or if you think I should wait until the week after.
Oh, um, for our Friday 31st session.
Well, for because if I'm taking another full length, like should I take that full length on Thursday and then we meet Friday, or like
Um, yeah, we can do that. Are you thinking like of an alternative or something?
no, I mean I think that's probably the best bet.
Yeah.
Um,
So yeah, so I would say like to yeah, for you to finish going over that psych soc in cars, and this time it'll take you less time because you're just gonna go over, the ones you got wrong. And then go over like the content stuff that you got wrong and learn that content. And yeah, and then you can take your test whenever you want, like on Thursday if you want. And we can meet on Friday and we can go over either still like if you still have questions from like this test or from the content diagnostic or from this test content stuff that you learned that you have questions on or questions from like the actual test that you take on Thursday.
okay.
So yeah, I would say to continue what you're doing with the review, and then take that test, on Thursday, and yeah, maybe on Friday. The test that you just took, the well taken, the diagnostic.
Okay. Sounds good.
All right, awesome. So yeah, it'll just be the 150, and I will see you on Friday.
Okay.
All right, take care. Have a good like weekend, and whatnot.
Thank you.
All right.
Bye.